Assalamu alaikum.
عليكم
Welcome
السلام.
to today we have our fifth lecture in this course of probability theory and stochastic process. I sent to all of you this part one of this course, inshallah, which is related to the probability theory part. In the second part, we will go to the stochastic process or random process part and systems, or the probability models. So today, just I will go through the basics that what we have already given so far. And also I will explore with you this chapter 2. This, as I told you before, that this chapter is part of one book that I am writing, and it will be ready by the next year, inshallah. So you can see here that this is chapter 2. So we have probability theory that we have already went through them, and the concepts of probability. Then we give some code, and you can find in this chapter the detailed explanation. Of course, I did that on one of the previous lectures, but you can find it written, that the detailed explanation of every function, why we use it and how it works. Of course, in this book we use MATLAB and also or Octave and Scilab. So we use two different programming languages, but they are very similar, so you don't find that big difference between them. Then we went through this topic of the conditional probability and Bayesian theorem, and also we explain it in details, this topic, but you can find in the papers that I sent you in this chapter more examples. Of course, we solved a few examples in the lecture, but you will find much more examples here. So you can, this is example 5, and you can see that example 6, and many examples here, and also how to write the code of each example. Okay, and example 7. All these are related to the conditional probability. Okay. Then here you can see example 9, example 10. So many examples, because actually some of you asked me that they want to see more examples about how to apply these that theorems that we have already seen in the course. So the idea here is not to look to the solution, to just come the beginning, read the example, that assume random number generator that generates numbers 1, 2, 3. Generally, the probability of each number appears next is 1/3. Okay, except if the current generated number is 2. So if the current generated number is 2, in this case, the probability that the next number will be 2 is 80%. The other two numbers will appear with equal probability. Of course, it means that 0.1 for each one. Okay, then compute the probability that x equal to 2, the probability that x equal to 1. Okay, and write Octave and Scilab code to simulate this example. So you can see now when you read this example, try yourself to solve the problem. Okay, try yourself to solve it without looking to the answer. And if you wasn't able to solve it, then of course you can look to the answer, or you can compare your answer with the like exact solution or the model solution. So it is given here, as you can see. So also the code is written. So try to write the code yourself first, and then look to the answer also. Example 12, another example, which those examples are more, we concentrate more on this like conditional probability. Okay, on the conditional probability. So you can also see that marginal probability and example for it, and also random variables. We talked about random variables before, and we We explained what is the meaning of a random variable, and we said that it is a mapping between the event space and real number space. And then we have also examples for that. You can see that. So plenty of examples. You can find a lot of examples, solved examples. So you can actually try and also test your understanding by trying with all these available examples. Then after that, we explained also that we started with the random models, random variable models. So if we have only two states uncertainty, we mentioned that this is called Bernoulli random variable. And after that, from Bernoulli, we went to the binomial, which is more generalization for the Bernoulli. So it is not two states, but it can be the repetition of these two states many times, n times. And then we try to find the probability for that. Then we start also to give examples for this. And you can see here that too many examples related and solved examples actually. Hypergeometric random variable. And actually, I solved with one example in the online session, but here you can find even more examples that you can try, and also the written code. So you can test your analytical solution with the Monte Carlo simulation. Okay, another examples here. You can, then we went to the uniform random variable. I explained this in the online session already. And but maybe we gave few examples, but here you can find much more or examples that you can try, and you can also write the code. Then of course we went also through the exponential random variable. We explained it, and also we went through the. So actually, I am following the book in my lectures. Okay, so you can also follow the book. The slides, maybe they are very just briefly presented what we are giving, but everything in details is in this book. So try to read these pages like page by page. So you will get the maximum benefit by attending this course, by taking by reading these chapters. Gamma distribution and or Erlang or gamma. So also this was here, and I don't remember that I gave example, but there is example here, so you can see numerical example how to solve it, and also some code to every problem, not every example, but most of the examples, they are associated with Monte Carlo simulation. So in this course, this is actually my vision in this course. So it's not giving the concepts only. Of course, the concepts of uncertainty and probability is very important, and this is the major target or the major objective of this course. But beside that is how to handle or how to solve the associated uncertainties, not only with analytical analysis or analytical computation, but also with Monte Carlo simulation. So you will get the maximum benefit by attending this course. So maybe you don't feel it now, but when you come later to your thesis and to some practical application, so you will see that this skill of uncertainty thinking, and also how to evaluate it with Monte Carlo simulation, that you have very strong tool that you can apply not only in master thesis, but also if some of you get a chance to go to the PhD, so you will also use this eventually everywhere in your research. So it is really important topics. Then here we go. We went through the normal distribution, and we mentioned that the normal distribution is one of the most important distributions to express uncertainty, and also explain why. And then we have examples also with Monte Carlo and also with analytical solution. Rayleigh distribution, of course, Rayleigh distribution, everyone in wireless communication, they know it very well, because Rayleigh distribution representing the magnitude of the received signal in multipath channels. And here we explained why, how to find or the random or the probability density function of it, and also some simulations associated with that. Then we have Rice distribution or ratio distribution, where also it is very important in wireless communication because it represents the multipath channel when we have like line of sight or we have one strong path. We have a strong path, but also associated with many weaker like multipath. Then this could be represented by ratio distribution. And then also we went to the chi-square distribution and with some simulations as well. And we have here, and last thing that also I explained it last lecture is how to derive yourself, how to derive a distribution yourself. For example, if you have certain problem and you want to find the distribution of, if you remember that when we talk about the circle, and then you have a drop that just drop it randomly within that circle. So find the location of that drop, the probability density function of the location. So we mentioned that the probability density function could be represented by the distance from the center of the circle to that point, and also the angle theta, and this was explained here. Okay, so this is also more and more numerical examples. Okay, and here actually this one was not explained before, but it is also very important, is which I will explain today, is how to generate a random number if we don't have the probability density function of that number from the packages in the programming language package. So we know that in programming language like MATLAB or Octave or any programming language, usually we have ready-made random number generators. For example, if you made this in front of you now, this random N1, this rand gives you, for example, the uniform distribution from 0 to 1. Maybe I can write it here. So let me. I will share now the. Yes. No, maybe now you can see the. Okay, the written sheet or the whiteboard. So here we can see that, for example, if you want to generate a random number, from 0 to 1, this you can find in MATLAB, for example, or Octave, the command rand. Okay, and if you want, of course, now if you want it to be shifted, for example, to be from 1 to 2, I explained this before. So you can just add 1, for example, and if it is from 1 to 3, then you can multiply here by 2, and you can generate any uniform distribution with this rand. Okay, and also in MATLAB and Octave, they use rand n, and this rand n actually generates normal distribution or Gaussian distribution, and it is the standard. Standard means that it is zero mean, and unit variance. Okay, and if you want to have non-zero mean, you just add the mean that you want to add, and you just multiply with the square root of the variance that you want. Okay, so when you multiply by the square root of the variance that you wanted, and then add the mean, then you can generate any normal distribution. Exponential distribution, it is given with, like, if I remember it well, exponent rand. Okay, if you want to generate log normal distribution, I mean, many distributions could be generated, and you can find them, like maybe tens of them. They are available, and you don't need to take to be like to think how to generate them, because they are already available there. However, when you make your own research, you might reach to some situation that you have your own probability density function. And this is very specific probability density function that you cannot find in like already in packages. So how can you generate normal or random numbers that representing that random or probability density function? Okay, if I go just because I wanted also to show you how to read this from the chapter. So I go back to the chapter to see this, but so you can see now. Yeah. Yeah. So we know that the cumulative distribution function, I will just write here, use comment, yes, activate just the bin. So here you can see, this is the cumulative distribution function, which is given as f of x0 equal to the probability of x less than or equal to x0, as you can see. And this will be the integration of from minus infinity up to x0. So this is the way how to compute the cumulative distribution function. But we know that the cumulative distribution function is always between 0 to 1. Okay? We know that the cumulative distribution function result will be between 0 up to 1. 0 for the impossible case and 1 for the certain case. And because B probability is x less than or equal to x0, when x0 goes to infinity, actually there must be, because any random variable is between minus infinity up to infinity. So in this case, you will reach to 1. It is for sure that x0 limit, when x0 goes to infinity, this must be 1. Okay, then this result will be between 0 and 1. Between 0 and 1. Okay? Then the idea, which is very simple idea actually, that you can generate this random numbers x by taking the inverse, because we now we know that f of x0 is equal to u. U is between 0 and 1. This means that x0 equal to the inverse function, the inverse of the cumulative distribution function of u. Okay, this will be the inverse CDF of u. What is u? U is any number between 0 and 1. U is any number between 0 and 1. Okay, then what we can do is simply like that. In the code, when you write the code, you generate random number, uniform random number from 0 to 1. That's what you generate. This is u. And then you take the inverse cumulative distribution function of this u, then you will get the random number represented by this distribution. Let me explain this by example. Assume that during your research in your master or in your PhD, you came up with this probability density function. So you have this probability density function, f(x) of x equal to 1 divided by 4 square root x, and x between 0 and 4. Or maybe you have the distribution that I gave you in the previous quiz, not today quiz, but the previous quiz. It was f(x) of x equal to some like alpha times x squared, and x was between -1 maybe to 1, if I remember well. Okay, so now if you want to generate random numbers representing this distribution or this distribution, you will not find them. You will not be able to find package in a standard package that generate you random numbers with this distribution. How can you generate them yourself? The first thing that we do, we find f of x. What is the CDF of this function? Okay, so the CDF of this function, simply, it will be the integration Okay, of course you can start from minus infinity, but here it is given already that x between 0 and 4. So I will start from 0. Okay, no need to go to the minus infinity because it is already 0. So from 0 up to what? Up to x0. Up to if I put here x, I can put also here x, so it doesn't matter. So if I put here x0, I put here x0. Okay, but usually because we don't like to have the same like variable with integration and the parameter itself to be the same name. This is the reason that we prefer to put here x0 and x0. Okay, and from 0 to x0, it will be 1 over 4 is outside the integration because it is not variable in x. So it will be square root of x and then will be dx. Okay, and of course this is x of the power half. So it will be like 1 over 4 integration from 0 to x0, x to the power minus half dx. Okay, so now the integration, as you know, that you divide by this one and also you add 1. So it becomes simply that it will be 1 over 4 here, and you divide by 1 over half, so it will be minus 2 here. Okay, and then you will have this x as of half, and the integration limits from x to x0. Okay, so now you can take the integration limit, and then this what we will have. So we will have a square root of x0, okay, divided by 2. So here, of course, we will have plus because we add 1 and then divide by half. So it will be 2 over 4 is half, and we have square root of x. So now that's what we have. Okay, so this is f of x0. Now this equal to u, as I said, between 0 up to 1. Okay, what is x0 now? X0 will be, I multiply this by 2, it will be 2u, and it will be square root. I take the double, or I take the square of both of them. This, it will be 2u squared. Okay, which means that it is 4u squared. As you can see, x equal to 4u squared. Okay, now how to generate these numbers? You just generate the uniform distribution from 0 to 1, the standard uniform distribution, substitute them here, you will get x, as you can see. Sorry. As you can see here. So I just generate a random number for 10,000 random number. Of course, you can generate as size as you want. And then this will be u. U is random numbers between 0 to 1. And then I substitute it here. So x equal to 4u squared. Okay. Now I wanted to see how it will be the shape of that. So I draw it with using histogram command, and then that's what I receive. Actually, this is exactly the distribution that I have. It is 1 divided by 4 square root of x. Okay, and x you can see from 0 up to 4. Okay, so this is the way that you can generate any distribution. But the problem that some of those probability commutative distribution function, they are not easy to find. Some of them, they are very complicated to find. And to handle this problem, then we show next that another method to find it. So, but it is I didn't give the approve for that, but it is also very easy to generate. And also I gave, for example, one example about the distribution itself, that I want to find the random numbers and then how to generate them with this method. So this is only the code that you need. So you just you can save these codes for future use. So if sometimes that you need to generate random number and the probability density function is not standard, then you can use these codes to find them. Okay, so this is, for example, the code that I generate, and then those the histogram, and this is the ideal. This is the what should be the distribution, and you can see that they are fitting very well. They are fitting very well, and the code to generate this figure and everything, you can find it this code. Okay, so it is only few lines, actually few lines, you can generate this code. In the last lecture also, we started a new topic, which is the expectations of random variables. And as I mentioned, expectations is very important as well, because usually we cannot directly deal mathematically with random number. So if you have a random number x0, and this random number can be 0, can be 1, can be 2, can be 5, can be -8, and with each one it has certain probability. Okay, it is fact. This is what we can see. But usually your system, or for example your business, if you have business, so you are not looking. It is important, of course, to look to the instantaneous, like reward or revenue or losses or risks. It is important, but we are more interested in the average. So if you have a certain, let's say, business, and in this business, sometimes you get a reward, or sometimes you get profit, sometimes you losses. But what is important, the important thing here, that if you run this business for a certain time, what will be the overall? The overall is the expectation, is the average. If the expectation is positive, then this business is worthy to invest. Otherwise, maybe not. So it depends. Usually, we need always to look to this expectation of some function in a random variable, or in a random process. So this expectation is very important. It gives us the averaging. The averaging, for example, in mobile network, if you made a contract for for 4G network, and then they tells you that the peak of this data rate, for example, that you can get is let's say 100 megabit per second. This is the peak, okay? But actually peak many times is not that informative, because usually the operator will not tell you for how long time or what is the percentage that you will get the peak. So sometimes you can make the contract and you will never see this 100 megabit per second. Yes, the base station and your service on your SIM card, it should be possible to have 100 megabit per second. But this depends on what? Depends on your location, depends on the channel situation, depends on many other things. So I am more interested to see what is the average bit rate that I can receive. So if they tell you that, for example, if you have two options, one contract with 100 megabit per second peak, but the average data rate is 1 megabit per second, and you have another contract that gives you the peak data rate is 20 megabit per second, but the average is 10 megabit per second. For sure that I will go to this one. I will not go to this one. I will not go to this one, 100 megabit per second. I do prefer to go to this one, because this at least it gives you that the average that I will receive is 10 megabit per second. Or sometimes they gives you the median. What is the median of the data rate? So it means that half of the time that you will get at least that much data rate. So usually we are looking for some expected value or some statistics more than the individual random numbers or random variables itself. So this is the reason that this expected, or the expectations of random variables, they are very important in practice. Okay. Also, I explained in the previous lecture the concept from where it comes. So we started from this basic example of the grades that I explained in the previous lecture. Okay. So as you can see that I am starting today by going through the like a fast review of the previous topics that we have covered so far. Okay. So you can see here the expectations, and then we gave some examples, but you can find here even more and more examples. For example, here, the example calculate the mean and variance of the random process given by Poisson distribution. So you can see here, this is the solution for this example. And also we have code approve that if our solution is correct or not. Another example, determine the relationship between the parameter of Rayleigh distribution, and also it is mean and variance and median. So you can see that this is the solution for this example. So more and more examples that you can find the expectation of this distribution, that we have X is a Rayleigh distribution. Actually, if you want to solve this expectation using analytical solution, it is very challenging, and I cannot say that it is impossible to find it in a closed form solution, because I didn't check myself, but at least it will be very challenging and very complicated. But with the Monte Carlo simulation, it becomes only, like, as you can see, nine lines. Actually, if you remove the clear all line, it is only 8 lines that you can generate, and you can solve this problem with using the Monte Carlo simulation. Okay, another example here, it was given that about what is known as Cauchy distribution. Actually, standard Cauchy distribution, this is one of the distributions that they don't have the mean nor variance. They don't have mean nor variance. So actually, if you want to find the mean with analytical solution, it gives you a number. So there is no mean for this random like variable. Okay, and when you try to find the mean by Monte Carlo simulation, this will not converge to any number. Okay, this will not converge to any number. Okay, so as you can see that too many examples, a lot of examples. Actually, you have enough examples that to understand the topic very well. So this is also for the expectations, and then we talk a little bit last lecture about the conditional expectation. Okay, and okay, now also I introduced last lecture the multivariate random variable, which is the random variable which consists of 2 like random variables or more, 2 or more. Here we have X and Y, 2, but it can be like n random variables, and in this case we have this joint distribution. This is the joint distribution with n different random variables. And actually, this is what I am concentrating for the lecture today, after this fast review of what we have already taken in this course. So today we will concentrate more about this multivariate random variables, and then how could we handle such kind of problems. Of course, this is very important to have. For example, if you have multi-path channel, and then we have the direction of arrival of the channel, and also we might have also the strength of that path. So both of them, they can be jointly like random variables. Okay, of course, because here they are changing with time, so we can call them random process. But because we didn't start the random process topic yet, so let us talk about random variables. So in this case, we have joint distribution, x1 and x2. Here, x1 is the direction of arrival of the certain path, and here the power in that path, for example. Okay, so this could be seen as joint distribution. Okay, and if you want to see only the distribution of one of them, then I explained this last time, that this could be found by the integration over the other random variable. So for example, if I am looking to see only the distribution of y, I will integrate over x. If I want to have the distribution of x, I integrate over y. So this is the general form of taking one random variable from the other random variable, okay, or a probability density function from the other distribution function. And it is generally, even for the joint distribution, that the total area under this surface, now we don't have line or curve, now we have surface. Okay, for example, like this one. For example, now we have x and we have y. Then we have here f of x and y. So here you can see that we have surface. We have surface, not only line. So, but the total volume in this surface, under this surface, must be also 1. Must be also 1. So this is for the random or probability density functions. Okay, and also for the like joint commutative distribution function, as you can see, the joint distribution function, it is the same concept as the single random variable. So it will be the probability that x to be less than or equal to x0, and this comma means and y to be less than or equal to y0, and then you take the double integration from minus infinity up to y0, minus infinity up to x0, and fxy dx dy. Okay, and also we can find the probability density function from the joint CDF in the same manner. If you remember that, we can find f of x from f capital of x by taking the differentiation of fx0 with respect to x0, and we just substitute after you make the differentiation, you put x equal to x0. Okay, and the same way, so if you have joint distribution, it is exactly the same. So you take the double differentiation, one time with x and one time with y, of fxy, x and y. So this will be, this gives you the probability, the cumulative distribution function from the probability density function. Okay. I mentioned also in the last lecture, but very briefly, that the joint or the conditional probability density function is the same as in the same way in the standard probability. So the conditional probability density function, the distribution of x given y, is the same as probability of x and y, the joint distribution of x and y divided by the distribution of y, as you can see. And also, if you reverse the distribution of y given x, it will be fxy divided by fx. And actually, the Bayesian formula is also applied here. So, for example, I can say here that f x given y of x given y is the same as, so here it will be divided by fy of y, okay? And the other one, it can be here f of y given x, y given x multiplied fx of x. So it is the same Bayesian formula. It can be generated using the probability density function. Okay. Just a minute. So in case that, by the way, before I go to this formula, I just wanted to mention one thing here. So sometimes you have x continuous, x is continuous random variable, and y is discrete. It means that y is defined at discrete numbers. For example, at y0, y1, y2, it is discrete, but x is continuous. How could we make in this case? So in this case, it will be simply like that. So if it is x given y, it will be f of x given yi. Okay, but if you want to bring the reverse, that what is the distribution of y given x, in this case you need to use probability mass function, which is b of yi given x. Okay, so now when you make it that it is function in x, because x is continuous, we use probability density function. If it is the probability of yi, where yi is discrete, then we use the probability mass function. We will see examples about this in this chapter and also in the next chapter. Okay. The joint distribution, they will be the multiplication, as you can see them here, in case that x and y are independent. So if x and y are independent, then you can easily separate them. It is like the same concept of probability of x, probability of x and y equal to probability of x times probability of y, only if and only if x and y are independent. So the same thing applied here. So the joint distribution function can be separated in this way if and only if x and y are independent. Okay. Before we continue, let me go to the whiteboard so we can write a few things more here. Yeah. What I would like to say here, for example, if we have the assume that we have f of x and y equal to a for some constant e minus x plus y, okay? And here for example, x greater than or equal to 0 and also y greater than or equal to 0. So now this is a joint distribution between x and y, okay? But actually, you can see here that this could be also written as, for example, a e minus x times e minus y. And this could be seen that as like square root of a e minus x times square root of a e minus y. And now we can say that this could be f of x and this could be f of y. Then f of x and y equal to f of x times f of y. And those actually, they are like exponential distribution. It is clear that everyone is exponential distribution, and now they are separable. Then we can say that x and y are independent. X and y are independent. Okay, but let us take another one. So assume that f of x and y equal to some constant a times e. I put a here to guarantee that the double integration must be 1. Okay, so this a guarantee this one. So e of the power minus x times y. Okay, actually this one you cannot separate them. They are not separable. Then in this case, you cannot say that x and y are independent. Now they are dependent. They are dependent. And assume that x is greater than or equal to 0 and y also greater than or equal to 0. Okay, greater than or equal to 0 and y greater than or equal to 0. Okay. Actually, you can find what is the distribution of, for example, of x. If I want to see the distribution of x only, this will be the integration from minus infinity up to infinity, f of x and y, dy. So when we make the integration over y, I will have f of x. Okay. But it was given that x and y, they are greater than 0. So this will be the same as integration from 0 up to infinity. And I can take this a outside. Then we will have here e of the power of minus xy, then dy. Okay. And when you take the integration with respect to y, this will be a divided by, of course, you just divide by the differentiation of this y. So it will be like minus a over x. Okay, so the integration from 0 up to infinity, e minus xy. And when you substitute x with infinity, this will be 0. And substitute with 1, it will be minus 1. So the integration will be a divided by x. So actually, this will be the distribution of x for this if you take separated from y. Okay, so this will be the distribution of x alone, not as a function in y. And still here, of course, x should be greater than or equal to 0. And actually, here we can see that x is not defined, the distribution at x equal to 0, because we will have that infinity here. Okay, so let's go to the so this is the joint distribution, and then we about the expectation, it is also the same is applied. So if you want to take the expectation, okay, if you want to take the expectation of x and y, where where or you want to find what is the averaging of any function j of x and y. So again, you take the double integration of j of x and y, but here you need to multiply with the joint distribution of x and y. Unless x and y are independent, and in this case, it becomes easier because you can separate f x and y. If you have x and y, two joint distribution, remember that if x and y are orthogonal, then the expectation of x and y times y equal to 0. If the expectation of x times y equal to 0, then we have orthogonal random variables. If they are independent, then the expectation of x and y equal to the expectation of x times the expectation of y. Okay? And if they are uncorrelated, then the covariance, this is called the covariance function. The covariance function is the expectation of x minus mu x times y minus mu y equal to 0. This is called the covariance function. Okay, so you can see that every independent function should be also orthogonal. Every independent function should be also orthogonal, because if they are independent, then for this one, you can't separate them. So it becomes like expectation of x minus mu x times expectation of y minus mu y, and this will be 0, because we know that the expectation of x minus mu x equal to 0. Why? Because you can distribute the expectation inside. So this will be expectation of x minus expectation of mu x. We know that mu x is deterministic number, so it becomes as it is. And the expectation of x is mu x. So mu x minus mu x equal to 0. Okay, so they are independent if you can separate them. So when you can separate them, then so every independent can be uncorrelated. Okay, but the converse is not necessarily true. The converse is not necessarily true. I give you a simple example. If I generate random process x, okay, x is a random process or random variable, and I take y1 equal to cosine x and y2 equal to sine x. Okay, so it is very clear here that the expectation of y1 times y2 equal to 0. They are orthogonal because it is sine and cosine. But actually, you cannot say that they are independent. They must be dependent. Why? Because both of them, they are using the same function x or the same random variable x. So y1 and y2, they are dependent. If you know y1, you can exactly determine what is y2. So y1 and y2, they are dependent, but in the same time, they are orthogonal. So it is possible that we have dependent and orthogonal. But for independent, usually they are orthogonal. If they are independent, then they are orthogonal or they are uncorrelated in more like precise definition. So if they are independent, they must be uncorrelated. Okay, so this is that we need to remember, because some students confused in these definitions. You can see here that we have the same example that I explained. Now that fx and y is equal to a times e minus xy, and both x and y greater than or equal to 1. Here it was given why I gave them greater than or equal to 1, because in the previous one, when it was 0, actually, if it was 0, then I have the problem here. I have the problem of that a divided by 0 is undefined. So I will have hole in the integration. So this is the reason that it is more safe to say that x and y is greater than 1. So you can see here the exact solution, and you can find the value of a, you can find the probability that x to be less than or equal to 2, the probability that x greater than 5 and y is between 2 and 3, and all these definitions were given. The density function of x, the density function of y, the conditional probability of x given y. And here the question is, are x and y independent or not? Simply, actually, you can find this by multiplying f of x times f y of y. If it is the same as f of x and y, they will be independent. But actually, it is clearly that it is not. Okay, so here you can find the solutions in details. Okay, so here you can find what is the value of y, and then what is the probability that of x, and also the probability of x, and also for y, and also to find the fx of x. Okay, so because now we start from 1, not from 0, so we have e minus x above. Okay, so this will be the distribution of x, this will be the distribution of y, and of course this will be the conditional distribution. And now if you multiply f of x and times f of y, if you multiply these together, what you get, you will get this number. And this number, or this function is not the same as f of x and y, which means that x and y, they are dependent to each other. They are dependent to each other. And then we can find also the expectation of x as you can see here. Okay. And also the expectation of x and y together, so you can find them. So actually, many examples, many numerical examples that you can apply the concept. The concept is easy. As this is actually the reason that, if you remember, in the first quiz, I asked some questions about general math, how to find the integration, for example, x times e minus x dx. It is something that we talked before, maybe in math 1, math 2, maybe also in differential equations, but it is natural that if you don't use it for a long time, that you will forget it. So this is the reason that I put it in the first quiz. I want you to revise things, because what is left here is just calculus. What is left here is just, I give you the concept. I give you the concept. For example, E, I just write it here, sorry. I will write it here. So expectation of any function in x and y is equal to the double integration over x and over y, j x and y, times the joint distribution of x and y, dx dy. Now I give this as a concept. This is concept. This is the concept of finding the averaging of any function in two random variables, x and y, as the double integration. But what is left? What is after that? Calculus. What is after that is not probability theory, or it is not probability theory. What is after that is just normal calculus. You need to handle the simple integration, differentiation. For example, if I give you what is f x and y, maybe even and z also. This is CDF in 3 random variable, and I asked you find f, x, y, and z. This will be the triple differentiation of this. So you need to take the triple differentiation of fx with respect to x, with respect to y, with respect to z. What is this? This is calculus. This is not probability theory. This is not stochastic process. This is just simple calculus. Of course, it might not sometimes simple. So some integrations can be complicated. Of course, I know that. But you will not see like complicated integration in this course. However, I am expecting that you know the simple integration like this one, the integration by parts, which can be solved in 2 lines. So I expect that even if you forget it, so you should go back and try to practice yourself with the simple integration, with the simple differentiation, so that you need to revise, okay? Because this is calculus. I am concentrating more on the concept. I am trying to explain the concept very well. But what is left about calculus, so I'm expecting that you will cover it by yourself. That this gap, if you have some gap there, so you need to cover it yourself, okay? However, of course, sometimes I can also give some examples to solve. I will, for example, this was in the quiz. By the way, I am trying to have time. I started solving all the quizzes, and inshallah, by next week or maximum the week after that, you will have all model answers for all the quizzes I will send them to you so you can check the model answer. But for example, if I give you that x, y equal to sine x, for example, of course, the differentiation of sine is cosine. Okay, the integration of cosine is sine. We know that. Okay, but if I give you that y equal to sine inverse of x, and I asked you to find dy over dx. So how to find this? From simple calculus, we can say that x equal to sine y. So just make the inverse function. So in this case, but I'm looking for dy over dx, okay? So in this case, I will say that dx equal to cosine y dy. And then dy over dx equal to 1 over cosine y. So this is dy over dx, but I am looking as a function in x, not function in y, okay? Of course, this one is called secant. This could be secant of y. But I'm looking is as a function of x. So this will be 1 divided by cosine. Y is equal to what? Y equal to, it is given here, y equal to sine inverse x. So it will be sine inverse of x. Okay. We know that cosine square x plus sine square x equal to 1. This is a general equation. So it means that cosine x equal to square root 1 minus sine square x. So I just substitute this here. So it will be 1 divided by square root. Cosine becomes 1 minus, and sine of sine inverse, any function in it is inverse equal to x. This is general. So any function of function inverse of x is equal to x. So this will be 1 minus x squared. So actually dy over dx equal to 1 divided by square root of 1 minus x squared. As I said, actually this was, if I remember well, this was given already in math 1. In math 1 in university, we study these things, and actually maybe also in the high school. But anyhow, that it is natural that if someone don't or use it for long time, so it is natural that they will forget it. So, but it is good that to revise those basics from time to time, go base to the differentiation, to the integration, and try to just exercise yourself with the simple math, because this is not probability. You might need this to solve some probability problem, but it is not probability, this one. This one is calculus. So you need also to revise some calculus. Sorry. Is there questions?
ساين انفيرس ساين تربيع ساين انفيرس.
Sorry.
خلاص.
What is the question?
They are discussing the formula you just presented.
Okay. So I can return it back. So you mean yeah, this one.
Yeah.
This is always generally true that cosine square of any number x plus sine square for any number x is always equal to 1. Okay, and actually, if y this happen, okay, if you make a circle here, unit circle, okay, and in this unit circle we have this is r equal to 1. Because it is a unit circle, okay? And we have here any angle theta, okay? And now you can see this one, okay? What is the value here? What is the value? I will call it, for example, maybe A, and I will call this as B. What is A? A equal to 1 cosine theta. So 1 times, because this is the cosine theta, gives you what? A. What is B? B is B here equal to what? 1, because the here the 1 sine theta. This will be B. Okay. What is the length of the radius here? It will be A square plus B square. So A square plus B square equal to what? Equal to the length. And the length here is equal to 1. Okay. What is A? A is cosine. So it becomes cosine square theta plus B is sine. So it plus sine square theta equal to 1. So this is this formula is correct for any theta. So it is for any theta, sine square plus cosine square equal to 1. So, and based on that, you can actually convert from sine to cosine. So here we can say that, based on that, we can say cosine theta equal to square root of 1 minus sine square theta. So, is it clear? So this is actually the proof of that. Okay. There might be also other proofs as well, but we will not go through them. But maybe just to remind you a little bit about the exponential of complex number. If you remember that E, J theta, J is a complex number. This is equal to what? Equal to cosine theta plus J sine theta. Yes. What is the absolute value of EJ theta? Equal to 1. Okay. And the absolute value of this one is equal to what? Absolute value is equal to the real part plus the square of the complex part will be square root of cosine square theta plus sine square theta. This will be the value of this one, which is 1. So this is also another proof. Okay. So there are several proofs for this. Okay. Okay, let me share the chapter. Then we another form of the multiple random variables, or it is called sometimes multivariate or multidimensional normal distribution, is very, very important. And this one is the distribution. How will be the distribution if you have from x1 up to xn, every one of them is normal distribution, and every one it has like mean mu1. So x1 has mu1, x2 it has mean mu2, and so on. And also every one it has their own variance. So x1 it has variance of x sigma sigma x1 square, and for x2 we have sigma x2 square, and so on. In this case, if we have this joint distribution, if they are correlated to each other, so this could be defined like this formula. What is the determinant? What is Rxx? Rxx is called the covariance matrix. What is the covariance matrix? The covariance matrix, it gives us a matrix, just matrix here. Okay. For the first element, it will be sigma x1 square. So it is simply the variance. Okay. And what is the second element here? The second element is the covariance between x1 and x2. So here we should write expected value of x1 minus mu1 multiplied by x2 minus mu2. So this is the covariance between x1 and x2. This is the second element. What is the third element? The third element will be the covariance between first element and the third element. So it will be the expected value x1 minus mu1. I will write also the third element for you here. Okay, I will write it outside. Expected value of x1 minus mu1, okay, multiplied by x3 minus mu3. Okay, this will be the third element, and the fourth, the fifth, it will be the same way. Okay, now we come to the second row. In the second row, the first element, it will be the covariance between the first and the second. So it will be the expected value, sorry. So it will be the expected value of x1 minus mu1 times x2 minus mu2. Okay, so this is the covariance between the first and the second. What is the second element? The second element will be the variance of the second random variable. The third one will be the covariance between the second random variable and the third. In this way, we can build what is known as the covariance matrix, and it was given here. So you can see the diagonal element contains the variances of each random variable, but the other elements, the other element of the diagonal, they are the covariance between different elements. So the covariance between x1 and x2. Remember, if all x's here, they are independent, then all this covariance will be 0. Then what we will have? We will have only diagonal elements, sigma x1 square, sigma x2 square, up to sigma xn square, and the other elements here are 0. All the other elements will be 0 if x1, if all x's are independent or uncorrelated. Of course, uncorrelated is less strong assumption than independent, because we might have dependent random processes, but still they are uncorrelated. Okay, so here we assume that they are uncorrelated random variables. So this will have the, in this case, will be the covariance matrix. And in this case, actually, if they are uncorrelated, we can say that f of x1, x2 up to xn is simply the multiplication of x1 times x2 up to multiplication of xn. So this will be the like accumulated, or the total probability density function will be just the multiplication of these individual probability density functions, because they are independent. Or for Gaussian distribution, it is enough to be uncorrelated in order to give them like this independency condition. Okay, so this is the main thing, and this determinant is the determinant of the Rxx, the determinant of Rxx. So here is the determinant function that also this was in the quiz. If you remember that, if I give you any matrix, for example, simple matrix like 2 by 2, so it is like, let's say 5, 2, and let's say 2, 1. Okay, so the determinant matrix is you multiply the main diagonal 5 times 1 minus the other diagonal. So it will be 5 minus times 1, it will be 5. Okay, minus 2 times 2 minus 4. So the determinant function, or the determinant value of this matrix is equal to 1. Okay, in case that you have more than 2 by 2, of course, I will not bring them, not in the exam and not in the quizzes, but also it is easy to find for 3 by 3, but more than 3 by 3, it will be complicated. So if I have like, let's say 1, 2, 1, 0, 2, 3, for example, and 1, 1, 0, and then you will need to find the determinant, then you take this leading factor, so it will be 1 times, and this is the, you compute the determinant of each sub matrix. So it will be 2 times 0 is 0, minus 3 times 1 is minus 3. So it will be 1 minus 3, then minus 2 times, you remove this, and you have this, the other sub matrix. So it will 0 minus times 0 is 0, minus 3, it will be also minus 3, and then plus 1 times 0 times 1 is 0, minus 2 is minus 2. So you will have minus 3, minus 6 here, and minus 2. So it will be minus 10. So this is the determinant of this 3 by 3 matrix. If it is more than 3 by 3, it becomes more complicated to find the determinant, and then you need to use some like program packages, like some calculators they have to find the determinant for any matrix, and also, of course, in Octave or MATLAB or any programming package, you can use them to find the determinant function. But there is a special cases. For example, if you have diagonal element, if you have, let's say, 2, 3, 4, 5, and then I have the other zeros are, all the others are zeros. What is the determinant in this case? The determinant in this case is very simple. It's just the multiplication of the diagonal element. So the determinant in this case will be 2 times 3 times 4 times 5. This is the determinant in case of diagonal matrix, okay? Yes, so here we give also some function how to generate any multivariate random variables with any given covariance matrix. So we have ready function in MATLAB. It is called MVN, multiple variable random. So it is MVN, multivariable normal random distribution. So here you put the mean vector, here you put the covariance matrix, and here you put the number of elements that you want to generate. So it gives you like the all random variables with these parameters. So it is very easy to generate this multivariable random numbers with MATLAB, and also in Scilab, it is also easy to find. Okay, there is one example here. So I forgot to put the solution, but I will add the solution maybe today and send it to you, updated version of this chapter, because this chapter is still under revision. So I am adding and removing few things. So also please, when you read the chapter, if you find like typos or mistakes or numerical mistakes, just inform me. Okay, so I can improve and correct them. Then we went to the function of random variables. Of course, this was also explained in details in the previous lecture. Okay, for a single random variable. For a single random variable, you can see that many different examples are given here. But for the multiple randoms, this was not explained in the previous lecture. So this is what I'm going also to give today. However, before I continue, I will give you like 20 minutes. Okay, 20 minutes break, so you can relax, because what is coming is a little bit, we have like a lot of math that we need to do. So I want you to relax, take your coffee. 20 minutes. Today is 11. Now it is 11:30. So we come back at 11:15. Is that okay? Okay, then see you after 20 minutes. Okay, we'll come back after the break. So now we let's go back to the chapter. And as I mentioned before the break, that we want to study more about how will be the distribution in case of the function is function in more than one random variable, as we can see here. So we have, this is the original probability density function. It is jointly with many random variables from x1 up to xn. And now we assume that we have mapping or functions, which is also y1 up to yn, and every y is function in these random variables. So it is j1 of, so it is, as you can see, that it is j1 in x1, x2 up to xn. This is y1, and y2 is j2, x1 up to xn, up to yn, which is also the function jn up from x1 up to xn. We are interested to find the joint distribution of y's, which is y from y1 up to yn. I put it here like y, bold y, as you can see. So the idea, very similar to the way that we did in the single random variable case. In the single random variable case, if we go to see what was the formula that we derived, you can see it here. Yes. So you can see this is the formula that we derived, that the distribution of y in the single formula case is equal to fx, and we put here the inverse of y, and then the absolute value of dy over dx. Okay, so this is the, or of course you can put it like this way. So it can be dy over dx, and here you can put -1, which is the same way. Okay, and in case, of course, that you have multiple projection between x and y, you can add them that in this method. And actually, we explained this in the previous lecture. So now we extend this case for the multivariate or the multiple dimensional case. In the multidimensional case, we can prove that it will be exactly the same as we did before. So you can see that we have fx as before, and then we have j1 inverse of y, j2 inverse of y. It is exactly the same as we did in the single case, but now we have multiple case. And before in the single case, we have dy over dx absolute value inverse. Now we have the Jacobian matrix, and we have the determinant of the Jacobian matrix inverse. So this actually representing, or this gives us, this gives us the rate of changes of x of y with every x in the in the distribution, because we have y1 is equal j1 of x1 up to xn, and we have y2 is equal to j2 of x1 up to xn up to yn, which is equal to jn of x1 up to xn. The idea that we want to quantify the absolute value of these changes of each y with each random variable xi, x1, x2 up to xn, with each function as well. This could be done what is known as Jacobian matrix. The Jacobian matrix is given in this form. So you can see the first row is the differentiation of j1 with each x. So it is j1 with x1, j1 with x2 up to j1 with xn. The second row is the partial differentiation with the second function y2 with each element, differentiation of j2 with x1, j2 with x2 up to j2 with xn. And we continue in this way until we reach to the final integration of the final differentiation with jn with respect to xn. So you can see that this matrix is clear that it is n by n matrix. It is a square matrix. And then we need to find the determinant of this matrix. I explained the determinant before, how to find the determinant of this matrix. After finding the determinant, just you take the absolute value of the determinant and you take the inverse, then you multiply it in this function. So this is the simple way to find the joint distribution of differential or of any set of random variables. Okay, so let us take example. So for example here, they gave us this relation. So you have y1 equal to j1 of x1 and x2. This is the relation of j1 of y1, and this is y2. So y2 equal to x1 plus x2. And they told us in this example that x1 has zero mean normal distribution with unit variance, and x2 is exponential distribution with lambda equal to 1. Okay, so we have the distribution. They said that they are independent. You can see that they are two independent random variables. So we have f of x1. They said that it is Gaussian distribution. So Gaussian distribution with zero mean and unit variance is 2 by, of course, sigma equal to 1, e minus x1 squared divided by 2. This is the normal distribution with zero mean and unit variance. And for the second distribution they said that it is exponential. So it becomes, so it becomes like f of x2 equal to e minus x2. So this is the distribution, the second distribution. Now we are looking to find what is the distribution, the joint distribution of y1, y2, of y1 and y2, which is y1 is given by this formula and y2 is given by this formula. Of course, now the joint distribution between y1 and y2, they are dependent. It is clearly that they are dependent. Actually, y1 equal to x1 divided by y2, as you can see. So they are related to each other in this way. How could we find the joint distribution? You might ask why we should study these things. I mean, what is the purpose of studying this relation? Actually, this is what you will see. For example, even in digital communication or in wireless networks in general, or in business or whatever branch that you study, you will find such relation that you may know the distribution of the original random variables or random process. You know the distribution can be, or at least can be, let's say, proposed like normal distribution, and then we know the mean and variance of that noise, for example. And now we have relations. We have another relation between these ones and the output. So the output is connected to these with different equations. And then we are looking to find the distribution of y1 and y2. Once we find the distribution of y1 and y2, we can study many different things. For example, what is the expectation of y1? And what is the expectation of y2? What is the signal to noise ratio? What is the expectation of y1 squared divided by y2 squared? Any like stochastic or probabilistic measures we can do easily once we know this distribution. So finding this distribution is the key to find any like behavior of this random process or of this uncertainty. Okay, so now I showed you that it is very easy to apply, because what we need, actually, we need to substitute this y1 and y2 in this formula, as you can see. This is the formula that we are looking for. So now we know if x, we need to find the inverse function j1 and the inverse function j2, then to find the determinant function, okay, of Jacobian. That's what we can see here. So first, since x1 plus x2 equal to y1, then we can find what is x1 and x2. Simply, I can do it here if you like. So then we have, for example, y2, as I said, equal to x1 plus x2. Then y1 equal to x1 divided by y2, as you can see, because x1 plus x2 equal to y2. Then x1 equal to y1 times y2. So this is the first inverse function. This is the first inverse function of x1. And also we can find x2 the same, because x2 now, since we know that x1 equal to, x1 plus x2, we said that is this equal to y2, okay? Then x2 equal to y2 minus x1. x1 equal to y1 times y2, then it will be y2 minus y1 times y2. This is the inverse function. So x1 equal to j inverse of y1 and y2, and x2 equal to j inverse j1. Of course, this will be j2 inverse of y1 and y2. So now we have them here. We have both of them. It is very easy to find. What is the distribution of x1 and x2? They are independent, so we just multiply them together, as you can see here. So we have, this is for the first one, this for the distribution of x1, and this is the distribution of x2. Okay, so simply we can substitute for x1, y1, y2 squared, as you can see it here. And for x2, I substituted here that x2 equal to y2 minus y1 times y2. Okay, what is missing here? Missing is finding the Jacobian matrix. Okay, Jacobian matrix is very easy to find. It is just the differentiation of j1 with respect to x1 and j1 with respect to x2, then the differentiation of j2 with respect to x1 and j2 with respect to x2. So what is the relation? We know that this relation now, this is j1. You differentiate this with respect to x1, and then you differentiate it again with respect to x2. So it is easy to find. So this will be the differentiation with respect to x1 and with respect to x2. And then J2 is also with respect to x1. We said that J2 equal to x1 plus x2. So if you take the differentiation with respect to x1, the result will be 1. And the differentiation with respect to x2, the result also will be 1. So this is the Jacobian matrix of this function. Okay, what is the determinant? As I showed before the break, the determinant is you multiply the main diagonal minus the other diagonal, the multiplication of the diagonal. So it will be x2 divided by x1 plus x2 square times 1 is the same, minus the other multiplication, but here we have already minus, so it becomes plus x1 divided by x1 plus x2 square. When you add, you will have x1 plus x2 divided by x1 plus x2 square. So this cancels the square, then we will have, this will be the determinant function. Okay, what will be the distribution? The distribution simply will be the multiplication of the determinant of this function in this equation, but of course, remember all the time to substitute with a relation with y1 and y2, because the function now is related to y1 and y2. Then we x1 plus x2, we know that it is equal to y2. So we have here y2. Of course, you take the inverse, magnitude inverse, which means that it will be just multiplied by y2. So now we have the new distribution. This will be the new joint distribution between y1 and y2. With this distribution now, you can find any values that you need. For example, if you are interested to find what is the expected value of y1, okay, or what is the expected value of the multiplication of y1 times y2, this will be double integration, then y1 times y2, okay, y1 times y2, then multiplied by, this is constant, so I can take it outside the integration from 2 pi. Okay, and then will be e minus y1 square, y2 square divided by 2, e minus y2 minus y1 times y2 times the absolute value of y2 dy1 dy2. Okay, so you might say that, okay, this is quite difficult to solve with like by hand calculation. Yes, you are right. It is not that easy to find this one, but of course you can use some packages, or you can use a numerical solution to find this double integration, or you can use some packages that they can simplify this. For example, using Mathematica, or using the simple toolbox in MATLAB, or simple toolbox in Octave, that you try to simplify the relation. Okay, of course you can solve it also by Monte Carlo simulation, but the Monte Carlo would solve it for certain situation. So you can find the expected value for certain situation. It gives you the average, but solving them in mathematically, it gives you like a clearer vision about what is going on in this process. This could be physical process. It can be like a social process that it is represented by this uncertainty function. Okay. Another a problem here, that in this example, we try to derive the Rayleigh distribution. We know that the Rayleigh distribution, it is given in this way. y1 equal to the square root of x1 squared plus x2 squared. This is the Rayleigh distribution. Okay. Now, if I want to calculate what is f of y1, I know that this is Rayleigh distribution. Rayleigh distribution, okay? But I want to prove it. I want to approve it, okay? So what I will do, I will assume another function, y2, that equal to x1. You can, of course, put it y2 equal to x2. It is up to you. I mean, I just select any of them, okay? So after solving this, okay, after solving for f of y1 and y2, then I take the integration over all y2 from minus infinity up to infinity, f of y1 and y2 dy2. Then what I got the distribution of y1, and this will be the Rayleigh distribution. Of course, I give this example just to show you how can you solve problems if you don't have the mapping that's like equal the number of the random variables in the equation. Like this one, I have only single equation, y1 equal to square root of x1 squared plus x2 squared. How can I solve it with and finding the distribution of y1? Before I continue to show you how to do that on the page, so I can also give another way. So there's another way to find it. So the other way is to compute the CDF. So the CDF of this function, which is given like f of x0 is equal to the probability that for example y less than or equal to x. Okay, let me make it I try to do it here before we go to the whiteboard. But f of y0 equal to the integration of from minus infinity, because here is positive, by the way, so minus infinity will be 0 already, so I will put it just 0, from 0 up to y0. Okay, then it will be this y0. Okay, this will be the square root. Sorry, let me go to the, it's better to go to the whiteboard so it will be easier in this case. Yeah, so the idea here that we want to find the distribution of this function y equal to square root of x1 squared plus x2 squared. This is what we are looking for. And we know that x1 is normal distribution with zero mean and variance. Let's say that it is xx squared. And also x2 is zero mean, is also normal distribution with zero mean and the same distribution x sigma x squared. But x1 and x2, they are independent. x1 and x2, they are independent. And we are interested to find what is the distribution of y. This could be done in two different ways. One way is just put here as y1, and we define another y2. You can select either x1 or x2. For example, I put here x1. And then we apply exactly the same way that we did before. So we can find f of y1 and y2 of y1, y2 equal to, then as we know that, because they are independent, so it will be the multiplication for both normal distribution, but anyhow, I will put them now just f of x1 because they are already on the chapter. So then I put here the J inverse of 1 of y and also J inverse 2 of y, then multiplied by fx2, the same J1 inverse of y, J2 inverse of y. Then I multiplied this by the determinant of the Jacobian matrix, okay, of y, and then I take the inverse. This is the simple way that we can find the distribution. After that, of course, now I found the joint distribution between y1 and y2, but I am interested only in the distribution of y1. So I take the integration from of course, from minus infinity to infinity, but this y1 is always positive, so it will be from 0 to infinity, f of y1 and y2, and I take the integration over y2. This gives us the requirement of finding the Rayleigh distribution. Okay, the other way that I mentioned now, that we can find what is the probability that y to be less than or equal to certain y0. This is the CDF of y0, and the CDF of y0 will be simply like that integration of from 0 up to y0. Okay, then you put here the square root of x1 squared plus x2 squared, and you put here the integration of x1 times the probability density function of x2. Then you take the x1 and dx2. Okay, so now we have this the double cost integration from 0 to y0, y naught, because the square root here of x1 square plus x2 square should be less than or equal to y0, which means that x1 square plus x2 square should be less than or equal to y0 square. Okay, so you can put them like this, or you can define them together. So actually, if one of them is less than y0, both of them, then x1 squared, for example, should be less than or equal to y0 squared minus x2 squared, and you can substitute this in this integration. After that, after finding the CDF, you take the differentiation of this CDF with respect to y0 at y0 equal to y, then you get the Rayleigh distribution. But I can see that this one is easier to evaluate. This one is easier to evaluate, as we can see in the chapter. Stop here. Sorry. Okay, so now you can see here that what I did. So I just define what is x1 and x2. Then, of course, now if you take the square for both sides, it will be y squared, y1 squared equal to x1 squared plus x2 squared. Then after solving, you can see that this is the j1 inverse, and this is the j2 inverse. Okay, now we can apply to find what is the Jacobian matrix. So I differentiate this with respect to x1, j1 with respect to x2, j2 with respect to x1 is equal to 1, as you can see here, and j2 with respect to x2, it is not function x2, so it will be 0. After that, we substitute in the Jacobian matrix and then find the determinant. The determinant will be this one, the main diagonal multiplication, which is actually 0, minus the second one. So, but anyhow, we will take the absolute value, then we will get rid of this minus sign. Okay, so in this case, the Jacobian, this will be when we convert it to in terms of y1 and y2. Okay, so now we substitute. So we got, this is the joint distribution of y1 and y2. But again, I remind you that I am interested only in y1. Because of that, I will take the integration with respect to y1, and then you can see that this is with respect to y1. We take the integration with respect to, and I make just a change of variables to make the integration easy. Actually, I bought it here in this chapter. I want you to give some practicing how to make these integrations in closed form. So after that, we got this formula, and this formula actually is the Rayleigh distribution, formula. Okay. Another problem, that how could we find the distribution in case that we have y equal to x1 plus x2, like this one. You have the summation of two random variables, x1 and x2. What will be the distribution of y? So assume that you know what is the distribution of x1, you know what is the distribution of x2, but now I need to build what is the distribution of y. Okay, as you can see, I defined here y1 equal to x1 plus x2, and y2 equal to x1, to make it like 2 by 2, simply like that. Then I can find the Jacobian matrix. So it will be dy1 with respect to x1 is equal to 1. dy1 with respect to x2, it will be 1. Then dy2 with respect to x1 is equal to 1. And dy2 with respect to x2, there is no x2 here, so it will be 0. In this case, the determinant function, it will be 1 times 0 equal to 0, minus 1 times 1 equal to 1, then 0 minus 1 equal to minus 1. This will be the Jacobian matrix defined at this for this formula. Okay. Then we go to the substitution in the, as we know before. So if y, this will be the function of the joint distribution between y1 and y2 will be the distribution of x. And remember that here we have x1 and x1 equal to y1, equal to y2, and then x2 equal to y1 minus y2, because x1 plus x2, we said that this equal to y1, and we defined x2 equal to y2, or x1 equal to y2. But it is okay that if you define x2 equal to y2, you will get the same result. Okay, so it is up to you how to select the second one. But the first one, I am interested to find what will be the distribution in case of the summation of two random variables. This is very important because in wireless communication, for example, the noise is additive with the information. The information, it has certain distribution, and the noise, it has certain distribution. How will be the distribution of the resultant process? Okay, so this is actually is very well needed or required in many different applications. The summation of random processes or the summation of random variables. Even it looks simple, but actually we will see that the distribution of y1 is not that simple, as we will see. Okay, now I substitute this here. So it is simply substituted and multiplied by the determinant of the Jacobian matrix, and we take the inverse, but this one equal to -1, the absolute value of -1 equal to 1, then that's what we got. Okay, again, we are interested to the distribution of y1 alone. We are not interested in y2. y2, it is clear that it is equal to x1. I am interested only in y1. So the distribution of y1, by using this marginal distribution, I need to take the differentiation or the summation over the other distribution. So I take the integration of this one with compared to y2. Then what I got only y1. Okay, this is actually the result. But let us simplify it further. So what if x1 and x2, they are independent? Okay, so we have y equal to x1 plus x2, and x1 and x2, they are independent. They are independent. What will be the distribution of y in this case? So the distribution of y in this case, because if they are independent, that the joint distribution will be the multiplication, as you can see here. I substitute with the multiplication in the above equation, and then I got this result. Actually, if you look to this result, that the distribution of y1 equal to the integration from -infinity up to infinity, f of x1, okay, the distribution of x1, and we substitute here with y2, and then the distribution of x2, and we substitute here y1 minus y2, and I take the integration with respect to y2, then I can get the distribution of y1. If you look and focus to this equation, just focus to this equation that now I put here, okay? I will remove this one. Let me. Trying to take this away, okay. Now, again, look to this equation. This equation, if you remember, is the convolution. This equation is the convolution. Okay. If you forget the convolution, let me go to the whiteboard just to remind you a little bit about the convolution. Of course, no electrical engineering like graduate should forget what is convolution, because convolution is one of the most important concepts in basic electrical engineering, because actually it represents that if you have any linear system, the simple linear system, and you have input x of t, and this system has impulse response of h of t, and then the output is y of t, then y of t is equal to the convolution x of t convolved with h of t. And mathematically, this convolution is given as integration from minus infinity up to infinity. For example, x of lambda, h of t minus lambda, d lambda. And then you got y of t. Or you can reverse it, so it can be integration from minus infinity up to infinity, okay, of x of t minus lambda, okay, h of lambda, d lambda. So it should be the same result. So this is actually the relation, the convolution expresses the relation between input and output for any linear time invariant system given in this way. And for simplicity, if we want to solve this one, if you remember that if the signal is defined only at positive time, then we can use Laplace transform to solve this equation. Or if the time is defined at positive and negative, then we can use Fourier transform. And the Fourier transform says that if we take the Fourier transform of this x, we have x of f, then h of t, we have h of f, and then the output will be y of f. And in this case, we say that y of f equal to x of f multiplied, not convolution anymore, but multiplied by h of f. And we call h of f as transfer function. And x of f is the Fourier transform of x of t. And y of f is the Fourier transform of y of t. And again, if I am still interested in y of t, then I take the inverse Fourier transform. So y of t will be the inverse Fourier transform of y of f, which could be defined as the integration from minus infinity up to infinity at y of f times the exponent of j 2 by ft. Then we take this with respect to f. Then we got y of t. So this is just very fast, like reminder for you for the basic linear system. So this is from linear system, and this is again I repeat. So there is little part related to probability and the stochastic. The major part is related to calculus and calculations and system engineering or system or linear system analysis. So the probability part is not that big in this course. As I said, of course, I was able just to keep like 3-4 weeks talking about probability and giving you many like problems about there is a bag, and in this bag there is like 20 pole, and one is red, one is green, one is black, and replacement you take one, what is the probability that you get that? And I can make a lot of tricks in that, but it will not be that very useful for you in your study. So here we focus about the application of probability and uncertainty. So we don't want to lose very long time talking about different like basic probability parts and the tricks there. So it is better to concentrate on the applicable part. So now we found that if we have y equal to x1 plus x2, and x1 is a random variable or random process, and we know the distribution of x1 like x1 of x1 and the distribution of x2 like x2, and they are independent, we found that the distribution of y in this case will be the integration of f of x1, for example, of y2, because I'm looking, okay, here I call it y, I will put like y1, okay? So, and this will be the distribution of y1, f of x1, y2, times f of x2 of, it becomes like y2 minus y1 dy2. So in this case, I will have the function sorry, y1 minus y2. Okay, no problem. So this will be the function that we find that the probability density function of y1, which is the convolution between both distributions. So the distribution of the summation case will be the convolution between the distributions of the other independent random variables. So the idea here that what if we have y equal to, for example, x1 plus x2 plus x3 plus up to xn. What will be the distribution of y in this case? So the distribution of y in this case is called the fault n-fold convolution. It will be f of x1 of x1. Of course, x1 here should be j1 inverse of y, okay, of y, convolved with f x2 of j2 inverse of y, okay, convolved with fx3 j inverse 3 of y, and we continue in this way. So it is called n-fold convolution. The problem that even a 2 summation is hard enough to find by the convolution, because if you remember from the convolution integral, that it is not that straightforward to find. Of course, it can be easy if you have, like, for example, if x1 is uniform distribution, like from 0 to some value, for example, to 1, and the second one is exponential distribution, those are very easy to find by, like, using the convolution integral. But for other distributions, it can be really complicated to find, okay, especially if you have n-fold convolution. But we can prove later that if you have all these distributions or this summation are Gaussian distribution, then the summation will be also Gaussian distribution regardless of the number. So if you have, this is Gaussian plus Gaussian plus Gaussian plus Gaussian, then this distribution can be approved that it will be always also Gaussian. Okay, what is the mean of the new Gaussian? And for example, if I have y equal to, let's say, x1 plus x2 plus x3, okay? And I told you that x1 and x2 and x3, they are independent, and everyone is normal distribution, and it has mean mu1 and sigma 1. And I asked you to find what is the distribution of y. The first thing you must always keep in mind that the summation of normal distribution resulted normal. The summation of Gaussian is Gaussian. This will not be changed. And we will prove that mathematically next lecture, inshallah, next week. So now the expected value of y here, the expected value of y will be the expected value of x1 plus x2 plus x3. And this gives us as the expected value of x1 plus expected value of x2 plus expected value of x3. And this will be mu1 plus mu2 plus mu3. So this gives us the mean of the new normal distribution. Okay, what is the variance of the new normal distribution? To find the variance, I need to find first what is the expected value of y squared. Y squared will be the expected value, okay, of, you take this square, it can be x1 squared plus x1 x2 times 2 plus 2 x1 x3 plus x2 squared plus 2 x2 x3 plus x3 squared. I take this square. Okay, then I can make the expand the expectation in between because it is linear operation. So it will be the expected value of x1 squared plus 2 x1 times x2. We know that x1 and x2, they are independent. So it will be like 2 mu1 mu2 plus 2 mu1 mu3 plus expected value of x2 squared plus 2 mu2 mu3 plus expected value of x3 squared. Okay. Now I know that expected value of x1 squared, I know that this should be like a sigma 1 squared, because we know that sigma 1 squared equal to the expected value of x1 squared minus mu1 squared. So the expected value of x1 squared, I am trying to do it step by step, just because when you come back to this recorded lecture, you understand what I'm doing. So this equal to sigma 1 squared plus sigma 1 squared. So I can substitute them like for these values. Okay. Furthermore, since I am looking for sigma y squared, this will be expected value of y squared minus mu, the mean of y squared. Okay, the mean of y squared, it is given, this one. And the expected value of y squared, it is given, this one. So you can just substitute. It is a little bit long, but straightforward. So it will be like expected value of x1 squared, which is, as I said, sigma 1 squared plus mu1 squared, plus 2 mu1 mu2, plus 2 mu1 mu3, plus expected value of x2 squared, plus 2 mu2 mu3, plus expected value of x3 squared, minus mu y squared. Mu y squared, you take this and you take square for this one. So it will be minus mu1 squared minus 2 mu1 mu2. This is the reason I put it, because they will cancel each other. Okay, minus mu1 mu3 times 2, of course, mu3, then minus mu2 squared minus mu2 mu3 and minus mu3 squared. So you can see that 2 mu1 and mu2 cancel 2 mu1 mu2, mu1 and mu3 cancel mu1 and mu3, 2 mu2 mu3 cancel each other. So what is left here is simply expected value of x1 squared plus expected value of x2 squared, then plus expected value of x3 squared, then minus mu1 squared minus mu2 squared minus mu3 squared, that they are like given here. Finally, this one, as I said, this equal to, as we said, sigma x1 squared. Okay, then it becomes plus mu1 squared plus sigma x2 squared plus mu2 squared plus sigma x3 squared plus mu2 squared, and then minus mu1 squared minus mu2 squared minus mu3 squared. Every mu1 and mu2 squared will go away. Then finally, sigma y squared equal to sigma x1 squared plus sigma x2 squared plus sigma x3 squared. Okay, so this is the general result when we have y equal to x1 plus x2 plus x3, where x1 and x2 and x3, they are independent, and every one, it has a certain mean and certain variance. Okay, then the resultant will be also normal distribution or Gaussian distribution, and the mean of the new Gaussian distribution will be the summation of the mean of each one, and the variance for the new distribution will be the summation of the variance of each of those. So the new distribution or the new variance will be as it is given here. It will be the summation of the previous distributions. So this is I show it in the long way, in step by step, but because I want you to break this like this wall or the as an ice breaking. So you need to do these calculations with your hand to be familiar. Even you don't need it in the future, that because most of the calculations will be done by Monte Carlo simulation, but it is still important that to be familiar what is going on there. Okay, let me go back to that. Yes. Yeah, so that's the n-fold distribution. And then here we have another example. Determine the probability density function of the random variable y, defined as the sum of two independent random variables, x1 and x2. The variable x1 follows a uniform distribution from -1 up to 5. Okay, so it is uniform from -1 up to 5. Of course, here it means that the magnitude will be 1/6 because the area must be 1, while x2 follows an exponential distribution with lambda equal to 1. Okay, so now we are looking for this distribution y1 where we have x1 plus x2. You can see here that we just apply what we have given now. So we define y2. I need to define another y2 equal to x1. Then we have the distribution of x1 I have it as a rectangular, okay? And the distribution of x2, we have it as the exponential. Then we can find what is the distribution of y1 by the integration over, by the convolution integration. And in the convolution integration, if you remember that, okay, I just remind you a bit that, okay, I put it here. This is the first function from -1 up to 5, 1 over 6 here. And we have the other one is exponential distribution in this way. So, instead, the main difference between this convolution and the convolution in linear system, we have time. But here we have random variable. So we have here the random variable, which is given for x1, and x1 is the same as y2. And this is the other random variable, which is given as x2, and x2 is equal to x1 plus x2. So it is here y1, which is also given like x1 plus x2. Okay, so of course it will be shifted. Okay, and now when we take the convolution, if you remember that we take this one, we flipped it upside down, and we shift it to the left, and then we start to scan it to the right, and then we add the area of this sliding. And in this case, we will divide it into two parts. The first part from -1 up to 5, because here is 0. Here we have 0. I will close this one. Here we have 0, and less than -1 is also 0, as you can see. So the function is defined only between -1 up to 5. Then we can take the integration, the first part of the integration from -1 up to y1, and y1 is defined up to 5 only. Okay. After that, after 5, actually, we will not have any contribution from the uniform distribution unless we have the previous one, okay, the previous before 5. After 5, any value more than 5, it will be the summation of the exponential distribution plus the number generated by uniform distribution. So in this case, we defined it in this way. So this is from -1, I divided the integration into two parts from -1 up to 5. Then the second part is when y1 greater than 5, there is no contribution from x1, and all generated random variables will be the form of exponential distribution, as at least for this which is greater than 5. Of course, it has the contribution generated before. For example, from y1, for example, x1, we might have the result was 4. Okay, the result was 4. But what if we got y equal to 6? So I know that if this one is equal to 4, then the rest 2 is generated from the exponential distribution. The rest is generated from the exponential distribution. Okay, so because without the exponential distribution, the maximum generated number is 5. So this is what we try to do it here. So then we take what is after 5. We take, of course, from -1 up to 5 because it is already done, and then we take the integration after 5. So we do it in this way. So we keep it as y1. Then we got, this is the result for x greater than 5. Then the distribution for the exponential distribution, for the summation, y1 equal to x1 plus x2, this will be the distribution of y1. It will be 0 if y1 less than -1. It is impossible to be less than -1. Why? Because the exponential distribution is greater than 0, and this uniform is defined only greater than -1. So if y1 less than -1, then the distribution will be 0. In between -1 to 5, we have this distribution is the summation of the normal the uniform plus the exponential. If it is greater than 0.5, it will be this part only. Okay, so this will be the y1 if it is greater than 0.5. So that now if you take the integration, the total integration must be 1. The total integration must be 1. Okay, now what is given here is this formula. So they say that based on this formula, okay, find in this example, determine the cumulative distribution function corresponding to the resultant probability density function. It means that you use this one to find what is fx, fy1 of, for example, y0. This is what we try to find. And then actually simply we apply just the distribution from -infinity up to x0, and then we got this result. Okay, and yes, so of course that you can see that the summation of fx0 when x0 goes to infinity, that f of x0 must be 1. Another example that how to find the probability if y equal to x1 plus x2, that explained before, the same example explained before, that if you want to find what is the probability that y1 is less than 1 or y between 5 and 6, and finding the mean and variance of y and the expected value of the logarithm, of the natural logarithm of 1 plus y. So all of them, I can use them based on the probability density function. Based on the probability density function, I can find all these solutions. Okay, and finally, actually, what I did, as I said, now it is calculus. Now it's integration calculus. So it is y times 1 minus e minus y. So this is not a probability. This is just now basic calculus, how to find the integration, how to find the differentiation. So when you see multiple derivations or mathematical manipulations, so all these are just like math calculus. So it is not probability. It is not something that related to the probability theory, but is just manipulation of mathematical calculations. For example, find the expectation of len, okay, of len 1 plus y. So I take the integrations over 2 like interval, the first interval from -1 to 5, and then we have len times 1 minus e minus y plus 1, and then we have the second period from 5 up to infinity. Then we can find this len, and then you need to evaluate these two integrations. Okay, I show here how to handle the integration in details, so you can take it as practicing for these calculations. After that, I made Scilab code, and I find what is the probabilities, and I compare the probabilities obtained by Monte Carlo simulation with the probabilities obtained by the analytical calculations. Okay. Yeah. Sorry. The final thing today that then I will finish the lecture. The final thing today is this example. So what if we have y equal to x1 times x2, and you want to find the distribution of y? So now I am interested to find what is the distribution of y, and y equal to x1 times x2. The same way that we did before, I can define another y. As you can see, I defined y1 equal to x1. Then we found what is if y and y1 equal to the distribution of x. And instead here of x1, I put y1. Instead of x2, I put what is x2? x2 here equal to what? x2 equal to y divided by x1. And we said that x1 is y1. Then x2 equal to y divided by y1. This is what I did. Simply like that. And then we have the determinant of the Jacobian matrix. What is Jacobian matrix? Okay, Jacobian matrix, we know that y equal to x1, x2. This is the first function. Okay, and then the second function, y1 equal to x1. Okay, the first differentiate y with respect to x1. Okay, dy with respect to x1 is equal to x2. This is the result. Differentiation with respect to x2 gives you x1. And then the second equation, J2, differentiation with the second equation with respect to x1 gives you 1. The differentiation of the second equation with respect to x2 gives you 0. Okay, the determinant of this matrix, then x2 times 0 is 0 minus x1. So the result will be minus x1. Okay, but x1 equal to y1. Okay, and you take the inverse. and you take the absolute value. So it will be simply 1 by 1, as it is shown here. Then I substitute this in the original function, and then we will have this as the joint distribution. This one is the joint distribution of of y1 and y divided by y1. Okay, but I am looking only for the distribution of y. So the distribution of y, I integrate this equation with respect to y1, and then I got this equation. If x1 and x2, they are independent, again, I can separate this joint distribution of x, and it will be separable in this way. So it will be fx of x1 times f of x2. Okay, after that, there's another example that you find the distribution of y equal to the maximum between x1 and x2. So if I have y equal to maximum of x1 and x2, how can I find the distribution of y? So it is also given here, but I think it is enough for you today. We went through many different things, and also we review what we have taken so far. So maybe, inshallah, we will start with this example next week. And after that, I try next week to, inshallah, to finish all these probability parts. So because after that, the week after next week, we start the stochastic process and random process calculations and concepts of ergodicity for stationary process, and what is the impact if you have linear system and the input is a random process. What is the impact? How could we calculate the outputs and how to compute the outputs? Those basic concepts. And after that, we start the like probabilistic models, like Markovian model, for example, and such kind of models, which are very useful in order to solve like practical problems. But we try next week to complete this first part of probability. I send you this, and I will update you also with more pages later. We talk about also next week, inshallah, characteristic function. The characteristic function is nothing but is the Fourier transform of the probability density function. Because as I said, that if you have, just I give you idea before what is going to explain next week, inshallah, that if I said that if you have x1 plus x2, then the distribution of y will be the convolution of x1 of course of y, for example, and convolve it, or j inverse of y, j1 inverse, convolve it with x2 of j2, j inverse of y, j2 inverse of y. This convolution, as we show in simple example, it was not easy to evaluate. Because of that, they said that why we don't take the Fourier transform of fx of y1 and f of x2. If you take the Fourier transform of each of them, we got what is known as characteristic function, the characteristic function of the distribution. And then the characteristic function of y will be the characteristic function of x1 multiplied of the characteristic function of x2. And instead of convolution, we got multiplication in the same way that we did in linear systems. It becomes much easier to evaluate the summation of random variables and random processes. So this is the need for characteristic function, and we will explain also next week, inshallah, how to find the moment generating function out of the characteristic function, and how could we generate any moment from the distribution by knowing the characteristic function. The characteristic function is the Fourier transform, and we know already in tables the Fourier transform of many different like probability density function. So it means that if you like get the characteristic function, you can find easily the moment of any distribution. And this is very important topic that we will see it later. Okay, that's all for today. So if you have any questions, let me now stop the recording.